Right, hello, it's Lois Gray, North Island College. So this is Control and Instrumentation week 12. This is your last official lecture, but next week I'm going to go over some of the past papers. So what would be a good plan for next week is if you have a go at doing them yourselves and come in with any that you're struggling with or questions about them, because I won't have time to go through, I don't think I'll have time to go through all the questions. So probably better if you give me an idea of which ones you really need help with. Yeah? I probably won't do much on the knowledge side of things either. That's up to you to kind of study it. So especially today's lecture, which is about SCADA and condition monitoring and analog processing. There's no calculations involved in that. So it's really a matter of you going away and reading about it and understanding it and then being able to write about it, I guess, in the exam if you get asked about something. So most of you are working in an industry, so you probably come across SCADA systems and condition monitoring systems somewhere in your industry. If you haven't, one or two of you maybe haven't, maybe some of the guys that are listening in as well haven't. I'll talk a wee bit about that, but I'm not really an expert. I mean, SCADA came really into play after I left industry. The battery factory doesn't really use SCADA for very much, so it's something that I'm not that familiar with. Some of you might be more familiar with it anyway. I should hasten to add, you don't need to know a whole heap of stuff about this. You don't need to know how the different blocks work. It's really more having a sort of overview, being able to draw a block diagram of a SCADA system and just explain briefly what the blocks do, but not going into the detail of what the circuits are, what the communications standards are, or any of that. You don't need to know it in that much detail. This is just like an introduction to it, really. If you were going to study it in more detail, you would probably be more inclined to study the particular SCADA system that you're using. A bit like PLCs, we can teach you ladder logic, we can teach you stuff about PLCs, but at the end of the day, when you go to use a PLC system, you have to actually read about the one you're using because they're all just slightly different. And SCADA is a very overriding term for a whole range of instrumentation. We'll start off with the analog signal processing bit first. Has anybody any questions from last week? No. Have you done the self-assessment questions from last week? Should I start with them? Will we start with that, or will I start with will I do that last? What do you think?
I never did them.
Well, maybe we'll start with that anyway then, and just as a revision from last week, and then we'll go on to the signal processing. Right, so if I switch over, I haven't actually looked at them, so as I say, I was only back from Perth College yesterday, so this is going to be a bit more less organised than usual, but... So if we go into here, so I'm pretty sure there were questions from last week. I'll just check that though. I think there's one for every week. So it's quite important you do these because the instrumentation questions in the exam are based on these questions that are here. Well, certainly the calculation parts of them are anyway. And I mean, you'll see in the practice exams, there's maybe only one or two practice instrumentation questions. So obviously there's a very high chance you're not going to get something that's in one of the past papers. There's quite a high chance you'll get something that's from these rather than a past paper. Past paper for the instrumentation side is really just showing you the type of thing you might get as opposed to the actual subject. If you get any of the subjects we've covered. So, must have been this one. No, we haven't done that. Must have been a flow and depth one, was it? Yeah, that's what we did last week, wasn't it? But like I said, I haven't even looked at this, so hopefully you guys are going to know the answers, because I might not. Right. Like I said, I won't bother doing the calculation. In fact, you might all be calculation. The calculation ones, when you put your answer in, you get the answer on how to do it. So I won't bother going over that here. If you have any questions about any of these, just take a note of them. You can ask me next week or through the week or whatever. Any of the calculation type ones. I think these are all calculation, actually.
Question 5 now.
Yeah, they're all calculations. Well, this one's how do you work it out, I think, is it? Water, 1 degrees. If the flow is assumed nominal and fluid is incompressible with negligible friction or viscosity, so basically a laminar flow without any losses, calculate the difference between V2 and V1 when the differential pressure is 20 kilopascals. So this is from Bernoulli's formula, obviously. We know that the velocity in this bit's faster. So that's why they do two parts first. There will be 2 minus v1 squared plus 20. Can't actually remember how to do that. So do you know how to do this one? Being the only mechanical person.
I think it's C.
I think it'd be two.
No,
It would be 2p, wouldn't it? Because you've got rho g squared.
It's
Oh,
D8.
rho v squared over 2. Yeah. I know that the.
So yeah.
So let me write on here, but I'm taking a bit of a guess here. But when you're from your Bernoulli's, there's a kinetic energy part. Is I don't know why that's not working. Yeah. So your equation is the kinetic energy part is rho v squared over 2 in your Bernoulli's formula, and then the other bit is just p plus p. So 2 squared. So I think when you rearrange that, that would obviously be plus p as well. But we're looking for the pressure difference, P2, P1. So if you rearrange that, I think you're going to end up with a formula where it will be V2 squared minus V1 squared equals 2p. The difference, P2 minus P1. Something like that. I don't know if that's exactly what it rearranges to, but there'll be a rho term as well somewhere. But anyway, that's what it's proportional to, so I think it'll be a 40. Does that make sense? Yes. Do you need to know this Bernoulli's formula? You won't be given that in the exam. But it's just made up of the different energies: pressure energy, kinetic energy, and height energy. Yeah? We did that last week. That's what you were saying, Sergio, wasn't it? So
Sorry.
I think it's probably the 40. V2 squared minus V1 squared is 40.
Yeah, well, it depends on the values that we have and we are given. But yeah, I think so.
Yeah, okay. Right. You copying that?
No.
Yeah, that's why I didn't know. We did that last week. So we think it's probably this one. And we know that V2 is greater than V1 because it's faster in this part, yeah? So let's go for that one. And that's the only one we can do without doing more calculations. That's right. Yeah. Okay, so I just figured that out. I didn't really do any calculation there. I just knew what the formulas were. Is that okay?
Good, Lois.
Yeah, that'll be all right. You'd be able to do that.
No bother, right?
Yeah. Okay, that's fine. Let's go on to the today's slides. So these slides are quite short, and also you've seen quite a lot of this stuff already. Click that. Like I say, if you have any questions about the calculation bits in the instrumentation, just ask me anytime. The answers are all there. So in terms of analog signal processing, the sort of things we're trying to do is remove the noise, reduce the bandwidth, amplify, probably linearize things like thermistors, which have very nonlinear responses. I showed you that a few weeks ago, and I told you why that was a problem. That's really about all you do in the analog world now. Nearly everything else is done digitally. Because in fact, filtering is mostly done digitally as well. And it's so easy to convert analog signals to digital signals. In fact, actually, I'll tell you, I was down in Perth to look at a wind tunnel down there, which is going to be quite a good project. The wind tunnel itself's not that great, but the idea is that we're going to be able to control that from Northanger College. So you can turn the wind tunnel on, well, probably not you, because it'll probably be after you've left. Some of you are here for another year, so maybe some of you maybe. Ideally, you'll be able to turn it on. A technician will put a little wing in the tunnel, because it's for testing aircraft wings. And then you'll be able to control the speed and everything else from a computer up in Thurso. So it's quite good, and all that's being done with digitization of the measurements, obviously. And then they're going onto the cloud, and then there's also like a LabVIEW interface to do that. So when I say things are all done in the digital world, that's the reason. It gives it much more flexibility, and you can do a lot more. I think that's going to be quite an exciting little project because it'd be quite interesting. I think the idea is going to also have a video so that it doesn't just look like a simulation. Because obviously if you just see a screen with dials and knobs and controls and things, you wouldn't know if that was controlling a real experiment or not. But if you can also see a video and you can see what's happening with your wing as you increase the wing speed, that will make it a bit more realistic. And you'll be getting real measurements as well, which is really good. Rather than, the problem with a simulation is you can get absolutely perfect measurements with no tolerances, no errors. So if there's a wee bit of turbulence in the real wind tunnel, you probably wouldn't see that on a simulation. You could simulate that, but it depends how good the simulation is. Obviously, if it's real, it's really happening, and you'll get all the errors and instrument inaccuracies and things that haven't been calibrated. So it's a bit more realistic. Anyway, that's the idea, mainly because I've got so many remote students. Make life better for them. Okay, so the sort of thing you've got effective noise on a signal. This is the signal we want. That's the noise. This is all stuff you know already. You'll have seen all this before. How could we get rid of that? Filtering, yeah. Filtering's the best way. High pass filter, low pass filter, any idea? Band pass filter? Band pass would work, yeah. Probably use a cheaper type though, which would be this is the signal we want. Is that low frequency or high frequency? Low. Okay, what's this noise?
High.
High, so we'd want a low pass filter. That means it passes low frequencies and stops high frequencies. That's what the term means, low pass filter. Yeah. If it was the other way around, which is a problem I often came across, was quite high frequencies had like mains ripple on them because a lot of things were powered by the mains. So you would have like the high frequency there, which is the thing you want, and it would be sort of oscillating up and down like that at 50 hertz. Then you would want the other kind of filter, a high pass filter, and that would filter out your mains noise. Or you could have a band reject filter. If you only have mains noise, and we'll look at them in a minute, there's a band reject filter which basically blocks the unwanted signal just at that particular frequency and lets everything else through. So that's the way filtering works anyway. And it all works with capacitors, really. Just because you know capacitance, most of you know that reactance of a capacitor changes with frequency. Same with an inductor. So you can design a circuit with inductors and capacitors in it that has a very, very high impedance at a particular frequency and a very, very low impedance at other frequencies. Yeah, that's it's as simple as that. It's really easy. So you don't need to worry about these formulas. You're not going to be asked anything about them, but that's the basic formula for a voltage noise source. Resistors are quite noisy devices. That's for a resistor. Yeah. So anytime you have a resistor in a circuit, you're introducing noise to it. Just be aware of that. And all circuits have some resistance with the wire. We don't really need to know all this stuff. I'm not sure why this is all in here. Shot noises are more random sort of noise due to current, not just related to resistors. So filtering is the main method. I just kind of explained that to some extent already. So the way filters work is they have a flat response over the frequencies of interest. So you can see here this filter's got 0 decibels gain, which basically equates to ×1. We've seen that already in the control theory lectures. So anything within this frequency band will come through that filter without being changed. Will be made smaller or bigger because it's just a ×1 gain. And then you get this sort of knee. This is quite similar to the responses you've seen on the Bode plots and things, yeah, in the control lectures. You get this knee point, and they measure what they call the pass band up to the point where that's dropped by 3 decibels. And that's always the case. That's always the definition of a filter pass band is always measured to the 3 decibel points. And then, depending on how many poles and what sort of filter you have, it'll either drop at 20 decibels per decade. How many poles would that equate to? 20 decibels per decade. You guys have done Bode plots. How many poles is that? 1, 2, 3?
1.
1, yeah. 20 decibels per decade is 1 pole. Yeah. There's 2, it would be going down at -40 decibels per decade. So you can obviously make this filter by adding additional capacitors and inductors, essentially additional poles. You can make that much steeper. So for instance, if you had a frequency here that you really didn't want to see any of at all. You would have to make that really steep so that that was pretty much a very low gain. Here it's still, minus 8 dBs or something, I don't know. Okay. This is called a first order one, which kind of ties in with your control theory. First order systems and poles and zeros and things. So that's a low pass one. That's a high pass one, just exactly the same idea. But this time it's got very low gain at low frequencies, and then at higher frequencies it's got 0 or times 1 gain. I think that's okay. That makes sense, doesn't it? Yeah, easy to understand, I think. Then you've got bandpass ones. These are like the ones on your radios in your cars. All right, it's all probably done digitally now, but in the old days, if anyone's got an old-fashioned radio, it was done just by moving the centre point up and down until you get the frequency of interest right in the middle. So the radio frequency that's being broadcast would be somewhere central there, and then other radio frequencies would be in these regions, so you wouldn't hear them. Okay? So if you didn't get that, if you were getting interference from other radio frequencies, it's probably because your filter wasn't narrow enough or didn't drop off quickly enough. And the frequencies were maybe quite close together. But anyway, so that's the way old-fashioned radios work with the tuning. They're a bit more complicated to design, obviously. And this is the one I was talking about, band stop filter. So if you have a specific frequency, like mains, 50 Hertz, you can design a filter that just cuts off that frequency but lets everything else through unchanged. Yeah, so quite difficult circuits. It's a kind of, I suppose, a subject in its own right, filter design, especially analog filter design. Digital is easier, but still used quite a lot. Used for things like radio frequencies still. My instrumentation amps, we've looked at these already. I told you it amplifies this differential part and doesn't amplify the common mode part. That gain's always 1 for that part. So that signals that are on both these inputs are not amplified. They just have a gain of times 1. But the difference between this point and this point is amplified. And the amplification factor is this value here, 1 plus 2 over RA divided by RG. You can either set these, some instrumentation apps you can set those, other ones you buy with a specific gain, with those resistors already set inside. To be honest, the ones that you buy are probably more common because you need to have these as quite high precision resistors. So they're normally manufactured into the device and kept very thermally close together as well, because you all know that resistors change with temperature. So if you want to keep these at a very set ratio, you have to have them quite closely thermally coupled so that one's not changing as the temperature changes and the other one's not. Yeah, kind of like your strain gauges. Okay, that's and we talked about common mode rejection. You looked at this already, so that's just 20 times the log of the differential gain. Linearization circuit, I'm not going to go into any details. This is almost always done digitally now, not very often done analog world. The only reason why you might want to do it in the analog world is if you had a very remote transducer, so maybe something measuring temperature in a furnace or something, and you obviously couldn't put your instrumentation in the same area. What you would probably want to do is linearize that signal before it got sent to your remote instrumentation. Because if you have a signal like this, and you're measuring something down in the bottom here, and there's some noise gets on that due to the sending distance, you're not going to be able to work out what temperature you actually measured. So it's a good idea, if you've got something remote, to do a bit of analog conditioning before you actually send the signal to the main instrumentation. Usually linearizing, usually amplification as well, so that the signal's a bit stronger and doesn't get so easily upset by the noise. Because any time you send thing a distance, whether it be on wire or whether it be through the air, there is a high potential for noise to get onto it and contaminate it. I'm sure you probably know that.
Does linearization change your output value? Is there a tolerance that...
Yes, it will do. You would have to know what the factor was. Yeah, because instead of getting this very small change, you're going to get a bigger change, so it will change the output value, yeah. But you would design the circuit so, or you would have a handbook telling you what like a calibration graph, telling you what the difference was. But yes, it does change it. Theoretically, it makes it better. I guess that's the idea anyway. So, like I was saying, this is quite often done digitally. You can do it very simply by the lookup table. So you just map each point on this curve to a point on that curve, and the digital processor will give you the output that you want. Or, again, also in digital signal processing. We're not going to really look at digital signal processing. It's too complex a subject for this level. If you go on to do the CNI 4 module, new one, there's a bit about digital signal processing in that. So an algorithm would just be like a quadratic equation, probably. So you would plug in the numbers from here, and again, you would get an output that looked more like that. Logarithmic amplifier. A logarithmic amplifier is the opposite response to that. It kind of does something like that, so it has the effect of straightening that out. It's like the inverse of it. Okay, what else have we got? That's it. You don't need to remember these, by the way. Anybody, instrumentation people, don't worry about it. Thank goodness. But just some ideas. Obviously, we talked about bias and zero offsets, and this is a way of removing them. So that's when your whole measurement is out by a factor, like your control experiment that we did with the flow rig. It was all out by a factor of about -0.4 or something like that, because the zero wasn't actually zero. So this is a way of removing that in the electronics world. You can do an integrator. You've already seen these, I think, with your PID. I think there was a brief picture of that in your PID notes. So that's a way of implementing the I part of PID. That's just a differential amplifier. Oh no, well, it's essentially a differential amplifier, but with a reference point instead of. So instead of subtracting those two, you're subtracting one from that, and then that from that. Sorry, that from that. If you want to do that, there's actually better ways of doing that. There's an actual comparator circuit you can use. So I'm not sure how useful that is. Summing amplifier. Anybody who's done the electrical principles one will have seen these, where all the different signals on here are all added together and then multiplied by the gain factor. Again, you don't need to remember that, just to show you some ideas of what is possible. You can think about this maybe if you're doing projects related to instrumentation. That's a picture of an analog transmission line. Again, I don't think, there's a lot in here you don't need to really know or remember. Because we still use analog transmission lines quite a lot, but if you're going to look at analog transmission lines, you probably need to look at digital ones as well, and that's a whole subject in its own right again, so it's a bit too much to cover here. You've got like all your standards, RS422, RS232, RS485, all your USB, your serial standards. So we're not going to go into too much detail, but just be aware that anytime you have two wires sending. Normally you'd have a wire and a ground or a wire and a return. You're going to have some resistance, some inductance and some capacitance associated with that wire. The people who've done electrical power, you did a more in-depth study of transmission lines in that, but it was based on the same principle. So even if you're transmitting high power, like thousands of volts, still the same idea. That the line is made up of elements of resistance, inductance, and capacitance all the way along. So if you haven't done electrical power, you're probably doing it next term, so you'll come across this in more detail next term. Mechanical people aren't doing that.
I don't think so.
Right, so we know that resistance causes voltage drops. Capacitors cause unintentional coupling, so at some frequencies these capacitors look like low impedances or low resistances. And you can get signals coupling between the two wires. And then inductors cause current coupling, which is actually less of a problem. So that's just an example of, 4 to 20 milliamps. How many people have heard of that? Yeah, most people here, I think, nearly everything at Dunray is on a 4 to 20 milliamp. Most of the instrumentation there is 4 to 20 milliamps. Why is 4 to 20 milliamps quite a good way of sending signals rather than 0 to 5 volts or 0 to 15 volts?
It's easier to tell in the fault, really.
Yeah, that's the main reason. Okay, so if you get a 0 in a 4 to 20 milliamp loop, you know that that's a fault. If you get a 0 in a 0 to 5 volt circuit, it could be a true measurement. It could just be that there's no no measurement there. So 4 to 20 milliamps is really good, because if the wire's broken at all, you're going to get nothing, and you're going to know straight away it's broken. Other reasons are because of the problem here of unintentional voltage coupling between wires. There's less of a problem with inductors and current coupling. So sending current is actually better. It's more immune to noise as well. It's also, most forms of noise tend to be voltage noise. So the equation for the resistor, it was a voltage noise source. So again, if you're sending current, there's less current noise sources that are going to contaminate it. So it's not going to get as affected by noise anyway. So that's a few reasons, but I guess the main one is that you can tell when it's broken. So, oh yeah, another reason, you don't require a stable voltage source. I'm not sure how true that is, because you obviously require a stable current source. So I guess both things do need some quite clever circuitry. Oh, that's another good point. It's not so sensitive to I times R drops. So wires obviously have resistance. And that's actually quite a big problem with your high voltage wires, which is why they pump the voltage up as high as possible. But if you're just looking for a current, that's not going to really come into effect. You're not really going to worry about the resistance at all. Capacitive coupling we talked about, open circuit being tested to 0 milliamps. Oh yeah, that's another good point, is you can have these at different earths. Because you're sending current, you don't have to have a reference voltage to be able to measure a different voltage from. You just measure the current. You need a reference current, but your reference current is probably 0 milliamps, so that's fine. This is something, again, that was quite useful when we used to test the radar, because we used to float the high voltage side of it at a higher voltage earth point. There wasn't an earth at all, it was just a high voltage reference. Compared to the low voltage circuits, we're all sitting at a ground reference. So by sending things between the two sections like this, the high voltage section and the low voltage section, you didn't have to worry about how you're going to connect a floating high voltage earth and a normal 0 volt earth, which you obviously can't do because that would damage the system. So this was a good way of doing that. The other good way is using things called opto-isolators. They form an isolation barrier between a low voltage and a high voltage side, but you won't have come across them. I talked about that already. So, just some pointers. If you are sending instrumentation signals any length, and they have to be sent as voltages, send them as differential signals, because then you can use an instrumentation amp to recover them, which is a very good way of doing it. Use a differential receiver, so that would be something like an instrumentation amp. If you twist the wires together like this, then any noise that's on one wire will be coupled to the other wire. So if you're sending them differentially, you can then filter out that noise through the instrumentation amp, because the comm mode gain is so low. Coaxial cable works in the same way, but it also provides a shield. This part here is an earth line. So this is quite good because it's not affected by radiated noise. You get conducted noise. I think have we covered this? No, maybe in power electronics or something. You get conducted noise which is sort of pushed on by a sort of voltage supply onto the wire. And then you also get radiated noise, which is noise that's just present in the atmosphere due to all these RF sources floating around, your phones, everything else. And that's radiated noise, and that can get coupled onto the cable just through the air, essentially. So if you put a shield around the wire, like this is doing here, then you're really making it immune to radiated noise. There won't be any radiated. That's tied to ground. So any radiated noise will go onto there and then just be conducted to ground, rather than being conducted to the wire, which is this wee bit here. So if you're ever working downstairs with the scopes, you've got your little BNC connectors that you plug into scopes. I don't know if any of you have used scopes. You must have done at some point in your life. That's all coaxial cable that's on the back of them. Yeah, and those little connectors are coaxial connectors. The ones you twist, as you put on. Okay, use screen cables. So there's a whole range of them. You can have single screens, double screens, kind of similar to that. You can have armoured screens. We used them quite a lot when the equipment was outside. You put like an armour and then a screen inside that. Comm mode chokes, you don't need to know too much about them, but they're just like circular ferrites, and you can wind your cables around them, and they just help with the coupling of the common mode signals, making them both the same on both sides, so they're quite good as well. You want to not load. So when you're thinking about the receiving end, you want to be sure you've got a high impedance. We talked about that with the instrumentation amps. You want to have a high impedance, high resistance receiver, so that you're not then making the signal voltage smaller. Remember, we're talking about sending voltages here. You want the signal voltage to be really big, so you get a big signal to noise ratio. Yeah? Does that make sense? Anybody got any questions? No? That okay? I don't understand that. I don't know how much of this you actually need to remember, just have a sort of overall knowledge of it. Right, that's the end of that. The other thing I quickly wanted to cover was SCADA. I don't open SCADA stuff. Things not there. It's here. Oh, here we go. Yeah, so I'll show you where all this stuff is actually, because you'll need to read this yourselves. Right, in your notes here, everything's organised in weeks, so things are quite easy to find. Under instrumentation, week 5, that's the bit about the stuff I've just covered in the slides, yeah? But you'll see further down, there's a whole folder on condition monitoring and SCADA. So I strongly suggest you have a read of the documentation in there and make some of your own notes. Because some of this is quite likely to come up in the exam. I'm not saying it definitely will, but it's a good question to ask in the section 3, for instance, because it requires you to have some knowledge and to be able to explain what you're talking about. So just make sure you have a look in there. And actually this document I was just going to show you comes from here as well. So that's notes I've written. And then these other ones are from sort of experts in the industry on these things. This one's a video, but it's quite interesting to listen to. I know videos take a bit longer to listen to, and people don't always like videos, but it's quite interesting. It's an expert guy talking about it. So I wouldn't bother necessarily reading that unless you're really interested in that. Anybody who's working in power might be interested in that, but other people can not bother. But certainly the rest of those ones are worth looking at. So the one I was going to look at just now was this one, Development of SCADA Systems. So you can read it yourself. I was just going to show you the block diagram. So, that's a bit off to the side of the page, but never mind. Is that big enough? Can you see that? I think it's really just to see the block diagram. So, that's a search. Yeah, that's better, isn't it? Okay, so that was an old-fashioned sort of SCADA system where everything... Oh, sorry, no, that's not the old-fashioned one. That's the new one. Here we go. This is a more old-fashioned one at the beginning here. So the idea with SCADA is that you have remote control and instrumentation sections that are completely autonomous, can work completely by themselves. So I think I might have mentioned this already. A good example is the Cozumel wind farm. In the Cozumel wind farm, every single one of those turbines has its own controller, its own instrumentation, its own... all the time the sensors are being monitored, the controller's adjusting things, it's maybe rotating so that the thing faces the wind, it's changing the pitch of the blades, it's monitoring for faults, maybe if there's an over-temperature condition, it maybe would slow something down or stop something. So every single one has its own independent control. And these are called remote terminal units, or sometimes they can just be PLCs, programmable logic controllers. Some of you might have done the HN unit on PLCs. But the idea is that we don't really want the system to completely work autonomously, because there might be certain times when somebody needs to interfere to do something. So, for instance, scheduled maintenance. If there's a scheduled maintenance coming up, you want to be able to go in and shut down that wind turbine. You don't want its own controller trying to keep it running. So the idea is that there is also a central monitoring station that is pretty much human operated. And that's why it's called SCADA. It's Supervisory Control and Data Acquisition. That's what it stands for. So this central monitoring point is acquiring the data from these remote terminal units all the time. So the data is being presented, so a human operator can look at the terminal. Have you come across SCADA? Some of you have, yeah. So the human operator can look at the terminal and he can see what the controller inside the wind turbine or whatever is doing. And he can look at all the data and he can look for any anomalies. Because sometimes, equipment goes wrong. Maybe the remote PLC's not detected it, or maybe it's something that's just showing a degradation, but it's not something that's bad enough for the controller to actually do something about. But a human operator can see that and he can say, oh yeah, that looks like that bearing is getting worse. I can see the vibration getting worse. So he might decide he wants to do something. And through this central computer, he can also control through the remote terminal units, he can control the equipment. So he could decide, I'm going to shut that wind turbine down because it looks like it's going to fail maybe in another week's time and I don't want to take that risk. So that's the whole idea of SCADA. It's not that the human is control all the time of the systems, it's just that he is able to take control if he wants to, and he is able to see what's happening. Now, with the Cosymire wind farm, I think the central computers are way down in Leeds or somewhere like that. So it's very much a remote system, and it's very much just a monitoring system, with the human only stepping in if there's a problem, or if there's something specific that he has to do. So the idea was, originally, we'd have the SCADA monitor, which was the interface to the person, and then we'd have all these remote terminal units, and then some wire using a wide area network between all the remote terminal units. And I think, in fact, the Cosymire is like this. I think it uses fibre optic cables. So all those wind turbines there are all wired up by fibre optic cable. It's quite an old wind farm. I don't know, can't remember when it was built, but it's been there for a while. So it uses a more old-fashioned type of SCADA. But of course, that's not really very handy. It would be far better if you can transmit the data wirelessly or over the internet or some other more fancy way. So I've got the second generation ones where you still have your wide area networks to your central server, but then you can have a number of operators connected together by a local area network, and they can all be working on it independently. Probably going to be in the same office, so they can talk to each other and not all try and do the same thing at the same time. But, you've got a few different people that can be doing things. I suppose maybe some might be controlling one section of the equipment and some might be controlling another section or watching another section. But then the more common kind now is this bottom one, where you still have your remote terminal units. There's networked remote terminal units, so still got your remote terminals or your PLCs, but they have a means of transmitting to the wide area network cloud, or basically the internet. And then through the internet, there's obviously needs to be a server controlling all that's going on. I don't know what that one said. That's a SCADA master, so I'm not sure what that does. You can read about that yourself. But anyway, so you can have your remote terminals anywhere with web access, and they can monitor these remote terminals, which are inside the equipment. They wouldn't normally look like that. They normally look more like a PLC or just a box. So, is there any problems with this, do you think? What sort of problems might you get with that sort of system? There is actually one major problem with it.
There's no fail-safe if a wide area network goes down.
Well, actually, that's a problem I hadn't thought about, but that's a good point.
Security risk.
There's also risk for
security.
Yeah, that's the two main issues with this. Is that we know hackers are really clever and they can get into anything. So you can try and make this a security-like, but there's always going to be a risk that it could be hacked, which could be very dangerous, of course, yeah? And in fact, I think in the beginning days of the Cosymire, it was actually quite easy to hack them, and some people did manage to change the turbine speeds and things. I heard, this might be just an urban myth, but you could do it with a mobile phone. in the early days. They've obviously improved the security now. But yeah, hacking's a major problem. And, you know, depending on what, if it's a nuclear power station, you definitely do not want somebody to be able to hack into that and do things to it. And as you say, the other problem is, yeah, your wide area network might go down. Your web might go down. That's quite common. So, or your power might go down. But I suppose the key thing about that, mind you, is that this is just a supervisory system. So you can actually stand to not have a connection for a certain amount of time, because the independent pieces of equipment will carry on working themselves. They do have their own monitoring and control remotely. So that makes that reasonably safe. But the hacking problem, maybe not so much so. Okay, so that's SCADA. Any questions about that? So the sort of things you need to be able to do probably is be able to draw some of these block diagrams.
Doesn't matter which generation?
No, won't matter.
How many marks would that be on as an exam?
I have no idea. If it's in
A
section,
big one, like.
if it's in section 3, it's probably 10 marks per question. So, but you do need to, you need to talk a bit about all the different parts if you're trying to get 10 marks. You wouldn't get 10 marks for a block diagram. I'm not saying it's in section 3. I can't actually remember. Honestly, I truly can't remember. But it's the sort of thing I probably would consider asking you about. And then the other bit is condition monitoring, which I think we've spoken about a little already, haven't we? Where I was talking about how you get your different maintenance. You've got your preventative maintenance, which is scheduled maintenance that you do on a regular basis. You've got predictive maintenance that you do if you see something degrading. So you can predict when it's going to fail and you can change it before it fails. You've got, I can't remember what the other one is, but obviously the maintenance that happens if something actually fails and you have to change it immediately. You remember what that's called? Sorry? Corrective maintenance, that's it, yeah. Okay, yeah. So you've got those 3 main maintenance methods. And you can use condition monitoring mainly for your predictive maintenance, yeah? Well done, Krista. Do you do that? Right. Yeah.
Okay.
Yeah, so the best one is obviously your predictive maintenance, but it's more expensive. I think we did talk about this earlier. So predictive maintenance is more expensive because you need your condition monitoring system. So it's got a high upfront cost. But the idea is that you can always predict a failure before it happens, so you avoid high charges because you need parts immediately. You can have a stock of parts that you know fail regularly. Or you can order the part, in fact it's better than that, but you can order the part in before it fails, so you don't need to keep a big stock. Yeah, and it's less risk in terms of safety as well, because you know when something's starting to fail, you can change that, and hence it's not going to cause some catastrophic failure. But I don't know how much that's used in industry, because I think it is very expensive. It would only really be used for sort of safety critical type applications. Anyway, we talked about that before. You can have a read of that yourself, and you can have a look at the video that I've put up on there as well. So, that's really all I was going to talk about today. As I told you, it wasn't going to be a very long lecture. Has anybody got any questions? No? You can ask questions. I might not be able to answer them, but you can ask them. No questions? Anybody got any questions about anything we've covered so far? Have you not really done enough revision to have questions yet? You have? Some. Okay, I can maybe come and speak to you.
Yeah.
Well, I don't know, it depends what they are. Maybe they'd be interesting to everybody.
No, I don't think they are too interesting,
Okay.
to be honest.
Well, we'll see. I'll speak to you later, and if they are interesting, we can look at them later, next week or something. What about the rest of you? Have you done any revision for these?
Yeah.
No. Yeah, did you say? Or did you say no? Right, so nobody's got any questions. You're all going to get 100% in this exam.
No, we just passed. That's it.
Okay.
30%, isn't it? 30%, isn't it?
As long as you've got more than 50 in between your 2 courseworks, yeah.
What's an average of 6?
What about the coursework? Is everybody well on track? I think the deadline's this
Friday.
week, isn't it? Friday. Yeah, no problems? No? Okay. Obviously too easy. I'll have to make it harder.
You can make it harder next year if you want.
Right. Okay, well, that's all for now then. I'll just switch off.
This call has been disconnected. Thank you for joining.